Hello and welcome to our discussion on the individual gas laws based on the combined gas law. Much of the research that was done by Robert Boyle and Jacques Charles and Joseph Louis Gay-Lussac, some of it was mathematical. Robert Boyle was one of the fathers of chemistry in the 1600s, and he came up with the association of pressure and volume. Um, By the way, make sure you're taking notes and following along closely with while we do this. There's a combination of concept and math we need to be comfortable with. But keep in mind that all these three laws, all three of them, are based on the combined gas law. So really and truly what we're doing is we're taking the combined gas law and we're going to be omitting one of the or more of the factors from the gas law. So these associations were made a long time ago. And essentially what it is not considering temperature, what happens between pressure and volume as you change one or the other. And it's found that the relationship is always going to be equal. So what we're going to do is put this little association up to say that as pressure increases, volume must decrease, and as pressure decreases, volume must increase. And we have this pretty piston with gas particles where the volume is halved and the pressure doubles. Okay, now I shouldn't say it that way. I should say the pressure was doubled and the volume of the system halved. Okay, you still have the same number of particles there, the temperature remained the same, but when you double pressure, your volume splits in half. And we define that as an inverse relationship. Graphically, what do we see from Boyle's law? Quite simply, if we graph pressure on the y-axis and volume on the x-axis, what we find is we get an inverse curve. Perfectly acceptable. That's exactly what we'd expect to see. In order to turn that into a linear relationship, we simply do we plot volume on the y-axis and the inverse of pressure on the x-axis. Now notice we've changed axes here to get a nice positive slope. Otherwise, we would have a negative slope. I hope you realize that and graphically why those things are that way. But what you should see is that when you plot pressure against volume natively, as it is, you get an inverse curve because there's an inverse relationship between the two factors. While if we plot volume against the inverse of pressure, we get a nice slope, in this case a positive slope. You can ignore the unknown or the constant K here. That's the topic that gets a little further along in chemistry. But graphically, I want you to be able to recognize that. So let's do a sample problem considering Boyle's law. A high-altitude balloon contains 30.1 liters of helium gas at 103 kilopascals. What's the volume when the balloon rises to an altitude where the pressure is only 25.4 kilopascals? So we have this flexible container, this balloon, and we're going to change the pressure and see what happens to volume. So at my initial P1 V1 is going to be equal to P2 V2. I've got 30.1 liters. I've got 103 kilopascals. And on the pressure side, on the second side, I've got 25.4 kilopascals. And I'm finding my second volume. So you can see the math here is fairly straightforward. The only thing I would be aware of is making sure your units match up. Units must align. So just note that kilopascals cancel and leave you with liters, which is exactly what you'd need to find a volume. And so then the operation then becomes 103 times 30.1 divided by 25.4. And our solution is 122.05 liters. So 122 liters for 3 sig figs. All of our factors had 3 sig figs. It was multiplication and division, so that's exactly what we would hope it to be. And it stands to perfect reason too. So if you noticed, pressure was cut in to 1/4 of what it had been. So we should expect volume to quadruple. The inverse of that happens to your volume. So your mental math should guide you here too to see that this is a reasonable response. Next is Charles' law. I spoke about Charles' law, and it was credited to Charles' law actually by our next scientist, Joseph Louis Gay-Lussac, because Charles didn't do a lot of work on paper with mathematics. He mostly formed associations, not more in a philosophical way. But nevertheless, Gay-Lussac credited this to Charles, named it for Jacques Charles because of his work that was never published. So the relationship between volume and temperature when pressure is held constant is Charles' law. So imagine our pressure does not change. What happens to our volume when you manipulate temperature? And we can expect this relationship, direct relationship. When you increase temperature, you can expect a volume increase. So let's look at the association here. As temperature increases, volume decreases. As temperature decreases, volume decreases. This is a direct relationship. So, moving on into the graphical relationship, I want you to see this. Pay no attention to the fact that this is in a different language. It's the same old deal. Thank heavens for the System International system of units. We can tell this is volume and temperature. So, what this graph shows us is the absolute relationship between volume and temperature. And what happens to volume as temperature drops. What I want you to note here is that you're getting down this perfectly direct relationship, this positive slope, eventually reaches a point where volume is 0. What temperature does that look like? Looks like around negative 273, doesn't it? That's called 0 Kelvin, or absolute 0. And we spoke about absolute 0 at the outset of the unit, about the temperature at which all matter stops moving and gases have no volume. That's it right there. But Charles' law is this relationship along that curve. Okay, it's a direct relationship. It's a positive slope. We don't have to do an inverse slope to get a straight line out of it. It's simply a direct relationship. As temperature goes, volume goes when pressure is held constant. So here's our relationship. You can see pressure and number of moles have been omitted from the equation. Let's do a little math. A balloon inflated at 24 Celsius has a volume of 4 liters. The balloon is heated at temperature 58 Celsius. What's the new volume if pressure is held constant? Now, we will not always say pressure is held constant. However, if pressure as a factor is not mentioned in the question, you can omit it. Okay? You can consider it constant and therefore omit it from the equation. So, my initial volume is 4.0 liters. My initial temperature is 24 Celsius, and we can't work in Celsius, so we'll add that to 273, and we will get 297 Kelvin. And we're looking for our new value when temperature goes up to 58, so then we'll do the same. Oops, let's just do it in the calculator. We have this handy-dandy calculator here. And we have a new temperature of 331. And we have our second volume. And then to collapse this down into an equation that will help us solve for what we're looking for, we'll multiply each side by 331 Kelvin. Note Kelvins cancel, leaving you only with volumes. And our operation then is 331 times 4. Sorry, not times, divided by, let's clear that up, divided by 297 Kelvin. And then Control Enter. There we go. So our volume 2 will be equal to 4.458, and we need just 3 sig figs. Keep in mind, this is still going to be 3 sig figs. When we add, sig figs are for the least valuable place value, and in this case it's the ones place. So we get to keep everything to the ones place. So we're going to keep 3 sig figs. We'll have 4.46 liters for our volume. Okay, and that takes us to Gay-Lussac's law. Like I spoke about, Gay-Lussac was actually responsible for naming Charles' law, Charles. And so what we see here is that as you hold volume constant, what happens between pressure and temperature? So volume held constant means our piston can't move. and this is a heat source heating up the gas particles inside this chamber. While they can't move, they are able to increase pressure because those particles all of a sudden moving faster and faster, having more collisions with the walls of the container, increasing the force over the unit area inside this container, which increases pressure. And so let's look at the word association here. As temperature increases, pressure increases. As temperature decreases, pressure decreases. And again, this is a direct relationship similar to Charles' law. So let's look at that graphically. What we see is a fairly similar graph, except now we're restricted to the point where we can get to a Kelvin zero again. This perfectly straight line, this positive slope, terminates where we have a pressure of 0, and that's going to be 0 Kelvin, or absolute 0. These points along the curve kind of illustrate the graphic we saw on the previous page, where as you increase the pressure value, or the temperature, the pressure inside the chamber increases. So again, we have a positive straight slope defining this relationship. So finally, one more math equation. Again, what you should see is volume's held constant, so it's omitted from the ideal, or from the combined gas law equation. The number of moles won't change unless we tell you it changes, and in this case of this question, it doesn't. The question states the gas left in a used aerosol can is at a pressure of 103 kilopascals at 25 Celsius. If the can is thrown into a fire, what's the pressure of the gas when the temperature reaches 928 Celsius? You might say to yourself, well, what if the can can expand a little? Well, let's just assume it doesn't. Okay, the reality is unless it's a very, very rigid container, it's probably going to have the capacity to expand a small amount. But we're going to assume that its volume remains constant throughout the process. Okay, our initial pressure 103 kilopascals at 25 Celsius, and keep in mind you can't work in Celsius, so we're going to add that to 273 to get our Kelvin value. That's 298 Kelvin. It's our initial pressure and temperature. And then if the can's thrown in the fire, what happens to pressure when we get to 928 Celsius? So 928 Celsius plus 273. It's a very large number. 1201 Kelvin. What's going to be our pressure? So the operation is identical to the last time. We're going to multiply both sides by the value in the denominator to isolate our variable. Cancel like units that appear in the numerator denominator and like values if they appear, and we end up with 1201 times 103 divided by 298 Kelvin. And our pressure is, again, 3 sig figs for each party. We have 4 sig figs in this one value here, but every other value has 3 sig figs. 415 kilopascals. When doing these operations, the one thing you need to make sure you're doing properly is that your units match up and cancel to give you the units that you're seeking. Lots of different possibilities exist. You're familiar with all the 4 different pressure values, temperature coming in Celsius and Kelvin. Volume can come in any metric volume measure, so be prepared to confirm that your units match. That is the last slide of this lecture. I hope you've taken some great notes and can come to class on Wednesday with any questions you might have. On Tuesday with any questions you might have. Otherwise, stay tuned for one more video where I'm just going to go through a few more math problems of different type. Just to kind of nurture you through the different sorts of math we can ask of you this unit. Have a good day.